Hi, listeners. This is the 80,000 Hours podcast, where each week we have an unusually in-depth conversation about one of the world's most pressing problems and how you can use your career to solve it. I'm Rob Wiblin, Director of Research at 80,000 Hours. Today, I'm speaking with a research scientist at DeepMind, which is probably the most advanced developer of machine learning systems around today. As you may know, DeepMind was the outfit that first beat top Go players with a system called AlphaGo back in 2016 to much fanfare. Since then, it has developed another ML system called AlphaZero, which can actually learn to play chess at the very highest levels with just 1 day of self-play on DeepMind's own processors. And more recently, DeepMind has been working on a system called AlphaStar, which now plays StarCraft 2 at the level of the world's top professional gamers. DeepMind itself says that its ultimate aim is to solve intelligence and develop a general artificial intelligence that can reason about and help humanity to solve any problem, basically. All of that is obviously very impressive and exciting, but regular listeners will know that I worry about how much we can ensure that AI systems continue to achieve the outcomes that their designers and the rest of us are pleased with as they become more general reasoners and are given gradually more autonomy to intervene in what is a super complicated world. Naturally, that is something DeepMind takes a big interest in and has been hiring researchers to work on. If DeepMind succeeds at their mission, the products that emerge from their work and research could end up making choices everywhere across human society, and even end up having more influence over the direction of Earth originating life than we flesh and blood humans do. So with any new technology as powerful as this one could be, it's really essential that we look ahead and devise ways to make it as robust and reliable as we possibly can. Unfortunately, that's just what today's guest is working to do. So here's Pushmeet. Today, I'm speaking with Pushmeet Kohli. For the last 2 years, Pushmeet has been a principal scientist and research leader at DeepMind. Before joining DeepMind, he was a partner scientist and director of research at Microsoft Research, and before that, he was a postdoctoral associate at Trinity Hall in Cambridge. He's been an author on over 300 papers, which have, between them, been cited at least 22,000 times. So thanks for coming on the podcast, Pushmeet.
Thanks.
I mentioned that I was going to be interviewing you on social media, and I have to say I've never gotten so many enthusiastic or question submissions from the audience. So unfortunately, for all of you, we're only going to be able to get to a fraction of those. I expect we'll get to cover how listeners might be able to contribute to the development of AI that consistently improves the world. But first, as always, what are you working on at DeepMind, and why do you think it's really important work?
So I joined DeepMind, as you just mentioned, 2 years back. And in the past, I've worked in a variety of different disciplines like machine learning and game theory and information retrieval, computer vision. When I first sort of came to DeepMind, I realized that the amount of work that is happening at DeepMind is just quite at a different order from what it is at other sort of institutions. And I quickly realized that making sure that the powerful techniques that we are building are stress tested and are robust and can be deployed in the real world is a topic of extreme importance. And all the sort of founders of DeepMind actually were very supportive of this particular view, like Demis, Shane, Moose. They're all sort of very clear on this path that we really need to deploy AI and machine learning techniques safely. And so that became the focus of my initial work, which is making sure that machine learning techniques are robust and safe when we deploy them in the real world. More recently, I was also made in charge of the science program at DeepMind, where the idea is we want to use techniques from AI and machine learning to accelerate progress in scientific disciplines. Science, we think, is a source of great sort of challenges as well as great opportunity. And it's one of the key tools that humanity can use to solve some of the key challenges that we are facing. So our AI for Science program aims to do that.
Yeah, so you're the research leader on these two different projects, AI for Science, as well as the secure and robust AI team. Maybe you could tell us a little bit more about like what exactly each of those teams does, and how do you balance your time like with so many responsibilities?
So let me start by the safe and robust AI team. The idea behind this team was to make sure that all the systems that we are developing and the tools and techniques that the machine learning community is developing can be properly sort of stress tested, and we can sort of check consistency with the properties that we would expect these systems to have. And if these systems are not behaving like consistently with our sort of specifications, how can we encourage them to behave or conform to the expectations of society? And finally, how can we formally verify that their behavior is consistent? Not just based on some statistical argument, but a formal mathematical argument where we can prove that these techniques will conform to the properties we expect.
So the statistical approach is kind of sampling and being like, well, most of the time it seems like it falls within these parameters, so that's fine. Whereas and like the formal one will be like proving that it can't fall outside particular bounds.
Yes, absolutely.
Talk a little bit about the AI for Science project, and maybe like what kind of things really excite you? What are the potential outputs from these projects that you think could really improve the world?
So science is a very broad area, right? Yeah. And it is one of the key sort of topics which gives us a way to understand about the world that we live in and even who we are. In terms of the topics, we have no sort of constraint on topics. We are looking for sort of problems in the general area of science, whether it's biology, whether it's physics, whether it's chemistry, where machine learning can help. And not just that machine learning can help, a way of doing machine learning where you have a dedicated team which works with conviction towards a very challenging problem could help. So if a problem can be sort of solved by using machine learning, off-the-shelf sort of machine learning techniques by some PhD student or some postdoc, then that might not be a good sort of project for us, because we are in this sort of unique position where we have some of the best and most talented sort of machine learning researchers, and we have the ability to galvanize these people towards one very ambitious goal. And so we look for projects where that approach really can make a difference.
Yeah. So what are some of the kind of concrete problems that you think machine learning can help with?
So one of the problems that we have already sort of spoken about is our work on protein structure determination. So if you know about like proteins are the building blocks of all of life, yeah, right? And everything about our own bodies is sort of informed by how proteins interact with each other. And they are like the machines. They are these sort of nano machines that are operating our whole body. We see the effects of it, but actually these micro machines are actually what are making us work. So understanding how they work has been a key sort of challenge for the scientific community. One aspect of that challenge is, if you have a protein which if you have specified as a sequence, can you figure out what would be its structure? Because in many cases, the structure actually informs what kind of work that protein does, which other proteins it will bind to, whether it will basically interact with other sort of agents and so on. And this has been a long-standing problem in proteomics. How do you infer the structure of proteins? And there are people who have spent their PhDs in trying to find a structure of one protein. So it's an incredibly hard and challenging problem. And we took it on as because we thought it can really, if we make progress in this area, it can have a very dramatic effect on the community. And so this is an example of one of the problems that we tend to look at in the science team.
Yeah, so if we manage to kind of solve the protein folding problem, I guess that helps a lot with designing medicines that have to interact with any proteins that are folding, and because then you know their shape, and then you can like potentially play with them.
So protein, as I mentioned, protein structure sort of informs protein functionality. That is the hypothesis. In many cases, it does. And then in terms of protein functionality, it has implications for antibody design, drug design, various different sort of very challenging problems that different scientific disciplines have been trying to tackle.
If listeners in 5 or 10 years' time found themselves saying, "Wow, like DeepMind made this amazing product that has like made my life better," what do you think that would most plausibly be? I suppose maybe it already is it's improving maps or improving like lots of services that people use online indirectly.
I think the way DeepMind thinks about this sort of issue is in an abstraction. Like intelligence is an abstraction. In some sense, it's the ability to solve many different tasks. And that sort of informs how DeepMind is structured, how DeepMind operates. We are not looking at one specific sort of task. Of course, we need tasks to ground the progress that we are making on intelligence, but we are working on this overall enablement technology which can enable a lot of different tasks. Yeah. So we don't sort of evaluate ourselves on what did we do on this particular task, but we generally evaluate us on what technologies did we develop and what did they enable.
So you're trying to do like more fundamental research into kind of general intelligence or like intelligence at a broader level rather than just single applications.
Absolutely. Yeah. But at the same time, I have to say that tasks are extremely important because they ground us. They tell us, they inform us how much progress we are making on this very challenging.
Disconnected.
Yeah, exactly.
So on the safe and robust AI team, I guess, what are some of the problems with kind of current or like near future AI systems that your research is hoping to fix?
Yeah, so I think this is something that the machine learning community as a whole is sort of thinking about. If you think about the history of software development, people sort of started off developing sort of software systems by programming them by hand and sort of specifying exactly how the system should behave. We have now entered an era where we see that instead of specifying how something should be done, we should specify what should be done, right? So, for example, this whole sort of paradigm of supervised learning, where we show examples to the machine or to the computer that for this input, you should provide this output. For this input, you should provide that output. You are sort of telling the machine what you expect it to do rather than how it should do it.
And then it's meant to figure out itself the best way to do it.
It has to figure out the best way to do it. But part of the challenge is that this description of what you want it to do is never complete. It's only partial, right? This is a partial specification of the behavior that we expect from the machine. So now you have trained this machine with this partial specification. How do you verify that it has really captured what you wanted it to capture and not just memorized what you just told it? And that's the key question of generalization. Does it generalize? Does it behave consistently with what I had in mind when telling it, when giving it the input-output examples? And that is a fundamental challenge that all of machine learning is sort of tackling at the moment.
Yeah, how big a problem do you think this is? And I know there's kind of a range of views, like within ML and outside of ML. But I guess some people think, this is a problem like any other, and we'll just fix it as we go. Whereas other people are more alarmed, thinking, no, this is like a really fundamental issue that like needs a lot of attention. Did you have any view on that?
I think machine learning sort of people have thought about. It's not as if it's a new problem. Generalization has been studied. The question of generalization has been studied ever since the beginning of sort of machine learning. Like, what are the inductive biases? What will machines learn? The question becomes much more sort of challenging when you put it in the context of the complexity of the systems that we are developing today. Because the systems that we are developing today are not simple linear classifiers or not simple SVMs. They are much more complicated, non-linear systems with variable compute and like a lot of different degrees of freedom. And to sort of analyze exactly how this particular model behaves or generalizes and which specifications it would be consistent with is a new type of challenge. So in some ways, it's the same challenge that we have always been looking at, but in other ways, it's a completely different part of the spectrum.
So I guess the concern might be that, as ML models have to like interact with the complexity of the real human world, trying to like actually act and like and improve things. There's like a lot more ways for them to act out of like how you expected them to than when they're just playing chess, where it's like a much more constrained environment.
Yes, absolutely. And I mean, if you think about software systems, right? If you are thinking about a software system for, I don't know, like you wrote a program in sort of BASIC or your first sort of program in C++, and you don't really care about like what it did, like when you're starting. But if that program gets installed in, say, an aeroplane,
or the electricity grid,
you should care, right? And so even the software industry has sort of considered this problem, right? There's a long history. You would sort of remember like what used to happen with Windows, the blue screen of death. It was sort of it was quite common. It was but it was a real technical challenge. Microsoft at that point of time was dealing with a lot of was building a sort of framework which could interact with various different devices. And it was a challenge to be able to deal robustly. And the last sort of 2 or 3 decades of work that has happened in formal verification, in sort of testing software systems, has come to the point that we now sort of expect the failure rate of these operating systems and so on to be extremely small. Right, it's not as common as we used to encounter in the 80s and 90s.
Is there a concern that when Windows 98 had a problem, it would do blue screen of death and stop? Whereas like, it's possible that machine learning algorithms, when they have a problem, they just kind of boldly go ahead and like do things that you didn't intend, and maybe you don't notice until later.
I mean that's sort of that is a problem that happens with software systems generally, right? So termination analysis, for example, is an incredibly hard sort of problem. How can you sort of verify that a method will terminate? And so if your software system does not halt, it is still a very big problem. It doesn't go away, right? So in some sense, I don't think we should have that distinction between normal software systems and machine learning systems. I think it is the same problem. It's just that software systems are also being deployed in mission critical sort of domains. Machine learning systems are beginning to be deployed in mission critical sort of domains. Software systems are complex, and machine learning systems are also complex, but in a different way. So I think the complexity is very different, and the scale is very different. The underlying problem is the same, but the types of challenges that appear are different. And as machine learning and AI sort of techniques are deployed in many different sort of domains, these challenges will become even more critical.
Is there any way to explain in kind of plain language the approaches to AI robustness that your team is working on?
So we sort of mentioned this particular view that when we try to test someone, one way to test them is basically ask them a bunch of questions, right? So suppose you are trying to test a particular sort of individual, you are interviewing them, you ask them a few questions, and then you use the answers and how they performed on those questions to get a good sense of who they are, right? And in some sense, you are able to do that because you have some expectation of how people behave. Right, because like you and I
years
are
of
both
experience with humans,
exactly, and because you are yourself a human,
you're right, okay,
right?
Yeah.
But when you are sort of reasoning about some other intelligence, then
like a bird, or
like a bird, trickier, then it becomes trickier. Even though we might sort of share the same sort of evolutionary building blocks for reasoning and so on, the behavior is different. So that comes to the question now: if there is a neural network in front of you and you are asking it sort of questions, you can't make the same assumptions that you were sort of making with a human. And that's what we see, right? In ImageNet, you ask a human, what is the label of this image? And even experts are not able to identify all the different labels because there are a lot of different categories and there are subtle differences. A neural network would basically give you a very high accuracy. Yet you slightly sort of perturb that image and suddenly it will basically, it will tell that a school bus is an ostrich, right? And so what we are trying to do is basically go beyond that simple approach of taking a few questions, the traditional sort of view of taking a few questions and asking those few questions. What we are sort of thinking about is, can we reason about the overall sort of neural network's behavior? Can we formally analyze it? Can we see what kinds of answers it can give? And in which cases does the answer change?
So that makes total sense. I guess you're like trying to like more formally analyze what is kind of the envelope of it, or like what's the range of behavior that a machine learning system can engage in, beyond just like sampling within like the normal range of questions that you might give.
Yeah. So the traditional approach would be that you take a particular input, and then what you do is basically you take that input and then you see how that input leads to activations in the neural network, and eventually the neural network gives you an answer. And then you can sort of see the path that the input took through the neural network to reach that sort of answer. What we are doing is we are saying we are not going to ask you one question. We are going to ask you a space of questions. And now we are going to see what is the response to that space of questions all throughout the network. So in some sense, we are asking the neural network infinite number of questions at the same time.
How do you do that?
So the way
a lot of compute.
So if you were to do it sort of naively, you would spend the compute of the universe and still not be able to sort of verify even a very small image network. Or even a sort of for an MNIST network, you will not be able to sort of specify even if you use all the computation in the universe. How we do it is by basically saying, let's try to encapsulate, or let's try to sort of represent that space compactly, not by those infinite points, but by certain sort of geometries which allow us to capture that space in some low complexity. Right. So now, like if you are trying to bound if you think about all the sort of points in this particular room, there are infinite of them, right? But they are bounded by just these four walls and the ceiling and the floor. So just these 6 equations of these planes bound all the infinite things that are inside this room, right?
So you kind of try to shrink the full space into like lower dimensionality. Is that the idea? Or
no, we are operating at the same sort of dimensionality. We are just representing that space compactly.
Okay.
Right. We are using fewer things to to represent that space. And now we are going to say how is the space of questions. So we have now. So there are infinite sort of questions in this particular space.
Yeah.
But the space itself is only sort of represented by, I don't know, like 8 equations or 10 equations, right? But there are infinite sort of questions that live in that space. And now we are going to see how the neural network answers these infinite questions.
Okay. Yeah.
Rather than just one question.
And then it becomes tractable once you define it that way.
Exactly.
So from reading a blog post that you published, I think it was a month ago, towards robust and verified AI, specification testing, robust trading, and formal verification, it's great that you have this safety research blog. I think it's on Medium. We'll stick up a link to it so people can check it out. There's a lot of great posts on there. It sounded like you don't only take that approach, you also try to like actively seek out the specific like niche cases where the system like might act completely differently from what you intended.
Exactly. So that's like adaptive testing. So the people who have given the SAT test or GRE would there is some sort of adaptive testing, right? So you answer one question, and then you're asked the question that you're asked depends on the answer that you gave, right? Yeah. So this adaptive way of questioning also is much more efficient than just I will pre-populate the 10 questions and you have to answer me the 10 questions. If I can choose which questions I'm going to ask you, depending on the answers that you've given me, then I'm more powerful in finding sort of places where you might be inconsistent or you might sort of give the wrong answer.
So you pose a question to it and then you get the answer, or you get a range of answers, then you choose the worst one and then you move from there and then like try a bunch of similar questions that are even harder and then like take the worst answer from that and then like keep going until you just find the most perverse like outcome that you can search for.
Yeah, so at a high level, at a simple level, this is how the technique works. But in some cases, you might not even know that in the first sort of question, the first answer. For example, you ask a sort of a car to drive from point A to point B. So what is the answer there? The answer is basically you look at how the car is driving from point A to point B. And just the behavior of how the car sort of drives from point A to point B gives you a lot about how the car is probably reasoning. So there is no perverse thing that it did. It basically did it correctly. But it gave you a lot of insights as to what might be that policy thinking about.
Yeah.
Right. And that informs your next question. rather than you selecting, going from point A to point B, point C to point D, and so on. So the next point that you decide is informed by you observing how the actual sort of car drove itself.
So how confident do you feel about these methods? You're like, yeah, we're killing it. We're going to solve this problem. It's just a matter of like improving these techniques.
Yeah. So if the answer is obvious, then it's not a good question for DeepMind to answer.
Yeah.
Right. So DeepMind is in some sense in a unique sort of position, right, where we are working in this ecosystem where there is academic research, there is industrial applied research, and then there is AI fundamental research. And we have our unique sort of strengths in the sense of how we are structured, the conviction with which we sort of go for problems and so on. So in some sense that always sort of forces us to ask the question, is this the most challenging problem that we can work on? Yeah. And is this the best way we can contribute to the community?
So you want to push the envelope?
Yes.
Yeah. There's another group at DeepMind called the Technical AGI Safety Team. Are you familiar with what they do and how it's different from your own work?
So the Technical AGI Safety Team reasons about AGI, right, where it talks about what are the issues that might come up as intelligent systems become more and more powerful. Right. And as basically systems become extremely sort of powerful, these questions of does the system align with my incentives? Like there are other sort of safety issues that come in at that spectrum. So the machine learning safety team and the technical AGI safety team are two sister teams which work very, very closely with each other. We share the techniques, but the problems that we sort of look at are at a spectrum, where the technical AGI safety team is looking at problems which are extremely hard but are going to happen in a few years' time, while the machine learning safety team is looking at maybe sometimes using the same sort of techniques at problems which are happening today.
Yeah. So, what is the relationship between this like kind of nearer term AI alignment and the longer term like artificial general intelligence issues? Do you think that one is just naturally going to merge into the other over time as like the AI systems that we have get more powerful?
One would hope so.
Yeah.
Because it's all about like the fundamental issues are quite similar, right? So if you think about value alignment or specification consistency, right? We talk about these things in the near term and long term safety sort of regimes as in these ways, but at the basic level, the problems are quite similar.
Yeah, it's interesting. I feel like just 2 years ago, I heard a lot of people say that the short-term issues with ML systems are like quite different from the long-term issues, and working on the problems that we have now like won't necessarily help with the long-term issues. But that view seems to have become like much less common or much less fashionable. Have you noticed that as well, or is that just kind of the people that I know?
Yeah, I think there is a gradual sort of realization that many of the problems are shared. Now, of course, the long-term AGI safety research has some unique problems which the short term doesn't have.
Yeah. Did you know some of those?
One of the things is when we talk about specification at the moment, when we think about deploying machine learning systems, we are talking about in a very specific domain. So the specification language, the way we express what we want the machine to do, can be constrained. The language needed for specifying what the behavior should be can be limited. But when you talk about an AGI basically can solve any problem on the planet.
In principle.
Yeah. Right? So then what is the language in which you specify?
How do you communicate?
To that very powerful sort of agent?
Yeah.
Is a unique sort of challenge.
Do you think we'll end up having to use like human language? Is this like the most like high bandwidth like method of communication that we have with other people? Maybe it's the highest bandwidth method we have with like an AI system as well.
So it goes back to the question that our intelligence evolved in a particular way. And in some sense, there is a good coupling between human language and human intelligence, right? So what came first, right? But there is some sort of notion that human intelligence is able to sort of deal with the concepts expressed in human language. Yeah. Now, a very powerful intelligence, a different intelligence, might have its own sort of language, might have its own sort of concepts, might have its own abstractions. But in order for us to sort of communicate between it, we'll need to either build a translator between those two languages, or somehow try to make sure that the intelligence that we are building conforms or is very similar to human language, so that it can understand the same sort of abstractions and concepts and the properties that we expect of systems.
Are there any other differences between the kind of work that you're doing and the work that the AGI, or any different challenges that the AGI team faces that are worth highlighting?
There are sort of at a very high level, the problems are quite similar, but the practical sort of machine learning systems throw up a number of different sort of issues, and some I think are shared, but like the question of privacy and security, and these are all sort of questions that are true in both sort of contexts. So I don't think there are many sort of problems which are different. The approaches and the problem instances might be sort of different, but at the basic sort of level, at the abstract level, the problems are quite similar.
Thinking of another, I guess, division between different kinds of work, I think one framing that a lot of people have about AI safety and reliability, that there's some people who are working on capabilities, like making AI more powerful, and there's other people, perhaps like you, who are working on reliability and safety and alignment and all of that. And it's like, I guess the extreme version of this view is kind of like, well, the capabilities, people are kind of creating the problem, and then like you're cleaning it up, you're fixing it up and making it better, and like solving the issues that are arising. And then impossibly on that view, you think, wow, working on capabilities is like possibly even harmful. It's just like not clear how helpful that is. I think this is a view that's like was more common in the past and is like has also been like fading. But do you have any comments on whether that's a good way for people to conceptualize the whole deal with ML progress?
Yeah, so that's a very interesting question, right? A lot of people sort of see ML safety work as sort of a tax, right? That you have to pay this tax to make sure that you are doing things correctly, right? Safety is sort of something that you want, like you don't want, like you like it's something that is sort of necessary. You have to do it, but you're not driven by it. I don't see it that way in some sense. So it's not, I don't think basically an organization which is doing safety work is paying a tax. In fact, it is to its advantage. So how do we explain this? So suppose you and me took a unique mission. And the mission was that we are going to drive a car around the planet. Okay. And so one approach is you sit in your car seat and you drive off without putting your seatbelt. And the other issue would be you put your seatbelt on. If we were just going from point 1 to point B and like maybe 1 kilometer, the probability of an accident is so low that you might actually reach the destination without putting the seatbelt on. Yeah. But if your destination is so far, we are sort of circumnavigating the whole sort of world. If we think about the probability of who reaches the end, you will see the person who put on the seatbelt.
Makes a meaningful difference.
Exactly. So it's about enablement. It's not a sort of a tax. It's basically enabling the creation and development of these technologies.
I can't remember who, but someone gave me this analogy to bridge building, where they're like, we don't have like bridge builders and then like bridge safety people who are completely separate from the people who build bridges. It's like, it's not a bridge unless it doesn't fall down. There's no like anti falling down bridge like specialists. It's like, that's just part of it. Yeah. I guess you're kind of saying there's like, it's not meaningful to talk about like building good ML systems without them reliably doing what you want. That's like an absolute core part of like how you design it in the first place.
Yeah, absolutely.
Is there any kind of steelman of this position that like, well, maybe we don't want to speed up like some sort of capabilities research. We might prefer to like delay that until we've done more of the kind of work that you've done. Perhaps we like want to like put extra resources into this kind of alignment work or reliability work, but as early as possible.
Yeah, so I think the answer to that question actually is very contextual. In certain sort of contexts, people have already sort of made that case. That when you try to deploy machine learning systems in very safety critical sort of domains, you ought to sort of understand what is the behavior of these systems. And in other cases where you are trying to do some experimentation or the proof of concept and so on, it's fine, right? To be able to sort of do that sort of stuff for fun and so on, and to see what are the limits of things. But I think there is a spectrum, and the answer is sort of contextual. There is no sort of clear answer.
Yeah, is it generally the case that work that improves like AI capabilities or allows it to like do new applications or have better insights also increases safety as you go, or also increases alignment as you go? Because that's just like part and parcel of like improving algorithms.
Yeah, absolutely. So in some sense, if you think about machine learning, what is machine learning sort of? I sort of think of machine learning as a translation service. So machine learning is a translation service where you bring it some specifications or some specifications of what behavior you want out of your system, and it translates it into a system which claims to have those properties, right? And so what is inside that box, inside that translation system? It has various different inductive biases, like either in the form of regularizers or different types of machine learning models which have different inductive biases and different optimization techniques and so forth. But all of those sort of techniques are essentially trying to solve this translation problem, converting your specification, which could be input-output examples or could be just the input examples in the case of sort of unsupervised or self-supervised learning, or it could be sort of interactions with the world, and translating it into sort of a classifier or a policy, depending on the problem type.
I imagine there's some listeners out there who know quite a bit about ML, considering doing careers in ML, and they would think that their passion is doing the kind of work that you're doing, or the work that the AGI team is doing. Imagining that they couldn't actually find, there's only so many people doing this alignment, reliability work. Imagine that they couldn't get one of those positions, but they could get some other general ML role to, improve their skills. But then they're like nervous because ultimately what I really want to do is the kind of thing that you're doing. What kind of advice might you give them? Will you just say dive in and you'll be able to, or kind of in any role you can find some reliability thing to contribute, or at least you'll be able to change into a more reliability focused role later on?
Machine learning generally and the robustness sort of problem are not sort of different from each other. In some sense, every machine learning practitioner should be thinking about the question of generalization. Does my system generalize? Is my system robust? So these are sort of problems that not
shows up everywhere.
This is everywhere, right? So the key sort of advice that I would give to people is when they approach the problem, they should not sort of approach it from the perspective of, well, if I take this particular input, apply this tool, I get this output. But think of it as to why that happens, or what are we after, and how will we get that, instead of, well, here's a very sort of systematic view of what needs to be done, but not how we should work, but what are we after.
Yeah, are there any ML projects or kind of research agendas that don't carry the label safety that you think are going to be especially useful for safety and reliability in the long term? People wouldn't think of it as an especially reliability focused project, but it turns out that actually it is going to have a huge influence on that potentially. Any that stand out?
So I think anything to do with optimization, right? So optimization is a general sort of area. It's not tied to robustness, or it's not tied to even machine learning. Right, optimization is used in a general sort of context for various different sort of problems in operations research, in game theory, whatever. And optimization is key to what we do. Optimization is a fundamental sort of technique that we use in sort of safety work to improve how our systems sort of conform to specifications. We are always sort of optimizing the performance of our systems, not to produce specific labels, but to conform to the more general problem of to conform to these general properties that we expect. Not to the simple properties of, well, for this input it should be this output. Well, that's a simple property. But you can have more sophisticated properties, and in traditional sort of machine learning, you are trying to optimize consistency with those simple properties, or reduce your loss, your empirical risk. And in our case, we are sort of reducing our loss or reducing the risk of inconsistency with the specification.
What do you think the general public or listeners, what would be their biggest misunderstandings about AI safety and reliability?
It's okay. That's a very hard question.
Because there's a lot of them, or just depends on who it is.
Yeah, it depends on who it is, right? I think one sort of interesting thing that people need to think about is, in the same way that we don't expect every human to be the same, we shouldn't sort of expect that every sort of machine learning system is the same. The second thing is that when we sort of test our machine learning systems, and when we sort of make claims about, well, our model performs very well on a particular data set, say ImageNet, or some other sort of data set for, I don't know, speech recognition, or you are solving that data set. Solving that data set does not imply that you have solved that problem. There's a difference between solving a benchmark or getting high performance on the benchmark versus solving the problem. And then the key question is, if solving a benchmark does not imply solving a particular problem, then what does? And that is a question where I think a lot more needs to be done, because that is the fundamental problem of what do we want or what do we expect out of systems? How do we articulate what does it mean to solve image classification or some other sort of problem? And that is where general public need to think about what is it that they're after and what do they expect out of these systems.
Before you were talking about this analogy between just like general software debugging and security and kind of robustness of AI, do you want to like expand on like what on that analogy and like what things we can learn from software safety?
So there are certain things that we can sort of learn. First of all, like even though it is incredibly hard, progress can be made, right? So we knew that solving the halting problem was undecidable, yet we now have very good tools for termination analysis. So that doesn't mean that we have solved the halting problem, yet it means that for certain instances, we can show that things will terminate, right? And programs do not just like hang all the time.
Yeah.
Right? They sometimes do, but not
less than they used to.
Less than they used to, right? So even though some problems appear incredibly challenging when you first look at them technically, over time you make progress and you find ways to somehow approximate what we are after. So I think that is a sort of good thing to learn from the software reliability issue. The other thing to sort of learn is when you think about defects in software, there are those defects. It's not enough to say that, oh, there is a defect, but nobody will find it. That is something that we should learn, because there are always people who will sort of find it, right? And
because they're actively trying, or just because there's so many people using something that eventually they run into it?
For both reasons. Yeah. So there is nature versus the adversary, right? So nature will find your bug, or the adversary will find your bug, and they will both use it, and you will sort of incur a cost for both cases, right? And so you have to sort of think about how do you want to make sure that your machine learning system is robust to nature and to the adversary.
So you think people kind of systematically underestimate how likely it is that the problems they know are in their software or their AI system will actually like materialize and create problems?
Yeah, so I mean, like nobody starts off by saying, "Oh, like I should write a software which can be hacked by some sort of hacker, and they can and use it to steal some information." Right? Every software engineer is trying to make sure that their program does what it says on the tin, right? But it's hard.
Yeah.
Right? Even after like decades of work, we still sort of see that defects or certain bugs in machine learning, or not like in normal sort of software systems, are sometimes exploited by people who can then use it for various different purposes.
Yeah, definitely. I mean, it seems like computer security is just kind of an unsolved problem and like a severe ongoing problem.
Yeah.
I guess, would you take from that analogy that like we could have just like many years where we're going to have issues with ML not doing what we want, and it's going to be like a lot of a real slog for potentially a decade or two before we can fix it up?
So in some sense, one thing that we have to take is we have to take it seriously. The second thing that we have to sort of take in is that we have to learn from history, right? There is already a lot of work that has already happened. And the third most optimistic thing that we can sort of take is that, yes, the systems that we are building are extremely sort of complex, but they're also simple in other ways. There's simplicity in basically the building blocks. And that simplicity should help us actually do much better than the traditional sort of software systems, which are messy in their own way.
Yeah, can you explain how they're simpler?
So we were talking about this whole idea of not asking the system one question, but asking infinite questions. So that technique of asking the machine infinite question, or reasoning about how it is going to sort of perform, not on just one particular input, but a set of input or a space of inputs, right? That is called abstract interpretation. in the software analysis and software verification community, right? And abstract interpretation, like when I was talking to you about in the context of sort of neural networks, because our operators are simpler in some sense. There are these neurons which behave in a specific way. We can capture what sort of transformations they are going to do to the input. While in a traditional program, there are so many different sort of types of operators. They have various different behaviors and so on. So you can do that as well, but it's slightly more complicated.
That kind of leads into my next question, which was is it going to be possible to formally verify safety performance on the kind of ML systems that we want to use?
I think a more pertinent question is, would it be possible to specify what we want out of the system? Because at the end of the day, you can only verify what you can specify. And I think technically there is nothing sort of course, it's a very hard problem. But fundamentally, I mean, we have solved hard sort of search problems and challenging and optimization problems and so forth. So it is something that we can sort of work towards. But a more sort of critical problem is specifying what do we want to verify? What do we want to formally verify? Right? At the moment, we sort of verify, is my function consistent with the input-output examples that I gave the machine learning system? Well, that's very easy. You can take all the inputs in the training set. You can compute the outputs and then check whether the outputs are the same or not. That's a very simple thing, right? No rocket science needed. Now you can sort of have a more sophisticated specification saying, well, if I perturb the input in some way or transform the input and I expect the output to not change or change in a specific way, is it true? And that's a harder question, but we are showing that we can sort of make progress. But what other types of specifications or what other type of behavior or what kind of rich questions people might want to ask in the future? That is a more challenging sort of problem to think about.
Interesting. So relative to other people, you think it's going to be figuring out what we want to verify that's hard rather than the verification process itself.
Yeah. Like how do you specify what is a task, right? A task is not a data set.
How do you have any thoughts on that?
Yeah, so I think this is something that, I mean, it goes into how this whole idea of sort of, it is a very philosophical sort of thing. How do we specify sort of tasks, right? And when we talk about tasks, we talk about in sort of human language. I can describe a task to you. And because we share some notion of certain concepts, right? I can tell you, well, we should try to detect whether a car passes by. And what is a car? A car has something which has sort of 4 wheels and something and drives itself and so on. And a child with a scooter, which also has sort of 4 wheels, sort of goes past, and you say, oh, that's a car. And you say, no, that's not a car. The car is slightly different. It's bigger. Basically, people can sit inside it and so on. And I'm sort of describing the task of detecting what is a car in these human sort of concepts that I believe that you and I share and a common understanding of, right? And that's sort of a key sort of assumption that I've made. Will I be able to also communicate with the machine in those same sort of concepts? Does the machine understand those concepts? Is a key sort of question that we have to sort of think about. At the moment, we are just saying, oh, input, this output, input, this output. This is a very poor form of teaching, right? If you're trying to teach an intelligent system, just showing it examples is a very poor form of teaching. There's a much more richer, when we are talking about solving a task, we are talking in sort of human language and human concepts.
It seems like you might think that it would be reliability enhancing to have better natural language processing, that's going to be disproportionately useful.
So natural language processing would be useful, but the grounding problem of, does a machine really understand
the concepts, or is it just pretend, or is it just aping it? Or?
Exactly.
Interesting. So that you think, is that a particular subset of kind of language research is trying to check whether the concepts the underlying the words are there?
Absolutely. That I think is and many people are sort of thinking about this key question.
How do we even check that?
So yeah, that's why we are all here.
Yeah. Interesting. I suppose you just you change the environment, change the question, then see whether it's it has understood the concept and it's able to transfer it and so on.
Exactly. I mean, that is a particular form of generalization testing, where you are testing generalization under interventions. So you do, when you intervene, and then you say, oh, now can you do it?
Yeah.
So, and in some sense, you are sort of testing generalization.
Forgive my ignorance, but can you ever kind of check whether a system is like, say, understands a concept by actually looking at the parameters in the neural net or something like that? Or is that just like beyond, like, it's like I can't like understand you by like checking the neuron connections, so we don't understand what that even means.
So it depends on the concept, right? If I can analytically describe a concept in terms of an equation, then I can do something very interesting. I can say, here is an equation, and now I will try to find consistency between that equation and how the neural network sort of operates. But if I cannot even analytically describe what I'm after, then how would I sort of verify?
Yeah. Okay. So if you designed a system to say do a particular like kind of arithmetic, then you could try to find. Then you could like we know how to search for that. Exactly. But if you have like a concept of a cat, not really.
Yeah. So now the question is basically how should we change the specification? Like what should be the specification language in which people can describe analytically things that they're after?
Are there any other parallels between robustness of AI and kind of software debugging and security that you want to highlight?
I think there's so many parallels that it's sort of difficult to sort of say. I mean, software testing has gone through its own sort of exercises about static testing and like static analysis and dynamic analysis. In static analysis, you look at just the software system and try to reason about it without even actually executing it. In dynamic analysis, you actually execute it, right? And so we do both kind of things in machine learning, right? We test, we actually run the model to see how it is performing, and in other cases we just look at the model structure and say, well, I know it will be sort of translation invariant because it's a connet. And a convolutional network gives us translation invariance. So I don't need to even run it to show that it's translation invariant, right? So there are sort of different types of reasonings that you can do.
Let's talk about predicting the future, which apparently is pretty tricky. How forecastable do you think progress in machine learning is? And what do you think causes people to disagree so much?
I don't disagree with many people, so I somehow think that people are talking about the same thing, but from slightly different perspectives. So, like in some sense, I don't find that there are so many disagreements. Even when people sort of try to portray that there are disagreements, sometimes if you really look deep inside the arguments, they're talking about the same thing.
I guess I was thinking that there's been surveys of asking like people in ML and related fields, when do you think we'll have an AI system that can like do like most human tasks at a human level, and just get like answers from like 5 years away to 100 years, 200 years, never, it's impossible. Yeah. It's like all over the map, and then just leave someone like me with like just totally agnostic about it.
So which is a very good example of what I mean by people are answering different questions.
Okay. So you think it's like question interpretation is driving a lot of this?
Exactly. Okay. So what does it mean to be human level, sort of be good at human level sort of tasks, right? Yeah. It is interpreted in different ways.
Interesting. So you think if you could get all of those people answering the survey kind of in the same room to like hash out exactly what they mean,
yes,
the answers or the timelines or the kind of
definitely it would
converge. Okay.
Of course, like some people would have different biases, right? They would have more information. Some would have less information, but I think the variance would definitely decrease.
So I guess do you want to comment on like what you think will like AI systems might be able to do in like 5 or 10 years that would be interesting to people? I guess someone submitted the question now. What's the least impressive accomplishment that you're very confident won't be able to be done within the next 2 years?
I don't know. Now again, it's a very subjective question as to what is the least impressive. Like somebody might say, well, changing a baby's diaper would be a very sort of it's something that everyone can do.
It's prosaic.
Yeah. But
on the other hand, very hard.
It's like who would trust a robotic system with their like I don't know.
Myself,
yeah, exactly. with a 6-month baby. So to get that level of trust for another intelligence, and we are talking about another intelligence, right? We can't make the same sort of assumptions that you and I like regularly make about each other, because we sort of think that they're like in some sense we are the same sort of. We have so many similarities in our DNA that we are going to think similarly or act differently, and we have the same sort of requirements. You would eat, I would eat. Like you need to sort of be there. Like when you're thinking about a different intelligence, you can't make those assumptions, right? And so it will be fine. Like to ensure to get to that level of trust is a very difficult thing to do.
One attitude I hear about in terms of like AI forecasting is kind of just people who read the news and they're like, my God, like these systems now, it's like it's killing it at Go. We're like killing chess. Like now it's playing StarCraft 2 at this. It's like doing these amazing strategies. It's like now we've got ML systems that can write, uncanny essays that like look like kind of they were written by a human, sort of kind of. Like, this is amazing. Like, there's so much progress. And then I guess I've heard other people who are like, well, if you put this on a plot and then you like map out like the actual progress, it kind of just looks like it's linear. Well, we've like thrown a lot more people at it. There's a lot more people working on ML than there was 10 years ago. And yet, like, in some sense, it seems like it's just linear progress in terms of the challenge, like the challenges that ML can meet. Do you have any thoughts on that? It's like, is ML progress kind of impressive at the moment, or is it just like what you would expect? And maybe do we have to throw more people at it because it's getting harder and harder to make incremental progress?
So my PhD was titled Minimizing Dynamic and High Order Energy Functions Using Graph Cuts. It was like some particular topic in function optimization, submodel function minimization, and so on. And when I was citing the papers in my thesis, I could find maybe like 50 or 60 very relevant papers, and they went from 1970s to the late 90s and so on. If you look at the same, if you do a similar sort of analysis for the type of work that we are doing now, the field is like growing exponentially. The type of things that we are sort of able to do is increasingly changing. And I mean, we are not in the same sort of context because the technologies that we have for research these days, there was no Google Scholar. At that point of time, people had to go to libraries or actually look at journals and see what is the relevant paper that was published in this journal. These days, like when you go to a conference, by the time you have reached the conference, the paper is already sort of old and you have like there are 2 or 3 iterations that have already happened. So there are a lot more people working in it, working on the domain. There are advances being made. Do we think that we can solve the problem completely? It depends on what is the definition of the problem. Yes, we can solve benchmarks very, very quickly, right? The rate of progress at which we are making on benchmarks is amazing. But I think the real sort of problem will lie in a problem definition. How do we define the problem?
Can you flesh out what you mean by that? Maybe not. You're like, the question is like, what do we want it to do, really, or
how do we measure progress?
Okay,
right. So we were talking about how do you specify a task, and then the question is how do you specify an associated metric?
To be a little bit facetious, I'm like, well, I want an ML system that can like do my job or can do whatever I do. That's too vague, I guess.
Yeah, exactly, exactly. So I think
that's the mistake that people make is
yes. I think basically once you've tried to formalize it, then it becomes very interesting because then you can actually measure it. And in some cases, machine learning systems are miles ahead, and in other places, basically, they're far behind. Like if you ask a translator, well, I want to do some sort of transcription. For example, a transcriber, right? Now we have machine learning systems which can do very, very fast transcription and quite accurately. But if the transcription quality was needed that like you are discussing something at the UN and there could be a war if something was not transcribed correctly, human will still do it, right? So I think those are the sort of places where your interpretation of the task and your interpretation of the metric becomes extremely important.
So you keep returning to this issue of like we have to be able to specify exactly what we want like properly. Yeah. I guess is that something that you think other people in ML like maybe don't like fully appreciate how important, how essential that is?
I think people do. Like most of the work in machine learning is about basically regularization and basically generalization and inductive biases. What are the inductive biases that basically certain regularizers have or certain model architectures have and so on. So people sort of deeply think about these sort of issues. Like you have some points, but how do you hallucinate between those points? Right? What happens? What is the behavioral system between those points or outside those points? Right? Away from those points. And that sort of key question of generalization everyone thinks about. But we were sort of thinking about it in sort of an abstract, sort of low dimensional sort of world where those dimensions sometimes did not have meaning. And now suddenly we are machine learning is in the real world where all these things have meanings and have implications, right? And failures of generalization along various different dimensions have different implications. And just coming to grips with that realization that actually whatever you do will have implications, and it's not about a generalization bound that you can sort of prove. It's about it that generalization bound has influence in society or has influence in how something will happen in the future.
Cool. Let's talk about some advice for the audience, so we can get like people helping you at DeepMind or work in other ML projects. If there was a promising like ML PhD student who for some reason just couldn't work at DeepMind, what other places would you be like excited to hear about them going to?
I think there is a lot of machine learning research happening across the board in academia, in various sort of industrial sort of research labs, as well as sort of labs like OpenAI. I think there is a general healthy ecosystem of AI research, and there is no optimal sort of place for everyone. Like there are different roles, and every organization is sort of contributing in its own sort of right. Some people want to really sort of impact I don't know, like a specific application, right? And it's good for them to work on that particular application and think about these questions that we were talking about. How do you actually specify what success means on that specification, right? Some other people could sort of say, oh, I'll sort of look at a more abstract level and think about what should be the language in which specifications should be defined, right? So there's a whole ecosystem, and people, it's important for them to work on sort of places which allow them to think about the problem, which gives them room to sort of develop themselves and learn about the area rather than just apply something known.
On that, how do you think academia compares to industry? I think you're briefly doing a postdoc at Cambridge before you went to Microsoft.
So I've supervised a number of sort of PhD students in the past, and I think academia and industrial research both have their unique strengths. So in academia, you have this very rich environment where you are exposed to a number of different ways of thinking, right? And then you have time to sort of reflect upon your own philosophy, your own way of thinking about things. It gives you a lot of freedom and allows you to basically gives you time to sort of build a philosophy. Compared to that with DeepMind. DeepMind also gives you some rooms to sort of grow and think about your philosophy and so on. But the unique strength of DeepMind is basically where you're working with sort of 20, 30 different people together. So collaboration is something which is key. If you go to an academic sort of lab, if your goal is basically to teach people or basically supervise a number of different students, then taking up a good academic sort of offer or good sort of or a teaching or research role in a university is a very good option for you. But if you would want to work on a very difficult sort of problem with peers, then sort of DeepMind becomes a very good role for you.
I imagine that you have some role in kind of hiring or recruitment for the two teams that you're involved with. Mm-hmm. I guess what reservations do people potentially have about coming and working on those teams at DeepMind, and what do you say to them? I mean, one might be they don't want to move to London. I was guessing that could be sometimes a sticking point for people.
So sometimes people have sort of family sort of constraints, and of course they want to be in the place where like they have certain sort of geographies they can be. DeepMind is also very flexible in terms of our geographies, but at the same time we also have to make sure that if there are projects which have critical mass, like, because that's how we operate. We operate in teams in sort of bigger projects which are focused, and so it's important for us to have critical sort of teams. So you can't have one person work on one particular team on one side of the planet working on the same sort of project with the other. So if there are sort of people, if there's a critical mass of people working on the project in a particular geography, that makes sense, right? But sometimes that doesn't work out for some people.
Yeah, I just moved to London and I'm really loving it a couple of months in. So if that's anyone's reservation, then send me an email and I can tell you about how great London is. It sounds like, I guess, a possible reservation that some people might have is that they don't maybe want to work in such large teams, or they don't want to work in such a teamy environment. Perhaps they're used to more like small group or like individual research.
Yeah, so I think that's totally sort of fair, and I think people have different sort of expectation and they have different preferences for the type of work they want to do. Right. If you are algorithmic sort of researcher where you want to spend your time sort of proving certain results of certain algorithms. You can do it anywhere, right? You can think about it. Of course, you basically feedback from peers and so on. It would be valuable for you, but you can sort of get that by traveling and sort of getting, like, you can still sort of collaborate with sort of people at DeepMind and so on. So it's not a necessary thing that you have to be part of a very big team. But if you want to say build the next AlphaGo or solve something really big, then you need to be part of a big team. So I think for those kind of people, like those kind of researchers really are attracted by the mission and the execution strategy of DeepMind.
So other than, I guess, passion for DeepMind's mission, what kind of listeners would be best suited to working here?
So one of the most important attributes, in my opinion, is the willingness and the hunger for learning, because we are constantly learning.
Is that because the technology is advancing quite quickly that you just have to always be learning new methods?
Exactly. So there are certain sort of roles in which you say, well, I went to university, I learned this stuff, and now I'm going to apply this stuff. DeepMind is where you are constantly learning, because we are continuously changing. We're making progress in our understanding of what's possible. So you're constantly sort of learning about new techniques, new algorithms, new results, new approaches. So you are sort of a lifelong student, right? So if you are comfortable with that sort of situation, where you really like to grow continuously in terms of in terms of your knowledge base, then DeepMind is a very good place for you.
Are there any particularly exciting projects or roles at DeepMind that listeners should be aware of that maybe they should apply for now or kind of keep in mind for the future?
I think DeepMind is sort of hiring a lot of different across the board, right? In sort of technical teams, in research teams, in engineering sort of roles, in communication, which is not just important for sort of making clear what we are doing to the real world, but also to understand how people perceive tasks, right? This whole question of like what are we after, right? So that's it. Not like one single researcher cannot sort of come up with the definition of what does that task mean. It is you have to communicate with people as to understand what they are really after in a particular problem.
Obviously we'll stick up a link to DeepMind's vacancies page so people can find out what's on offer, at least at the point that the interview goes out. So let's talk a little bit about your own career. It seems so you were like a rising star at Microsoft and now a rising star at DeepMind as well. How did you advance up the hierarchy in machine learning so quickly? And I guess especially starting from India, where I guess you've had to go overseas and build your reputation somewhere that you didn't grow up.
So I have been extremely sort of lucky in terms of getting some very, very good mentors and very good colleagues. I sort of grew up in India. I did computer science in my undergrad, and it just so happened that I had a very sort of good teacher who was in our automata theory course, and that got me really interested into formal methods and so on. And I did some sort of research during my undergrad years. And that led me to Microsoft Research in Seattle. And there I was working with one of the best teams in formal methods in the world. And I don't think any sort of many undergrads would sort of even dream of sort of working with the team. So I was extremely lucky to basically be interning with that team. And then I spent a lot of time in that group.
So they sought you out, right? When you were doing your PhD in India, I think, and Microsoft emailed you and tried to get you in this internship. I mean, is that normal?
I was not doing my PhD. I was doing an undergrad.
Right. Okay.
So apparently, at that point of time, Microsoft had started a research lab in India, and as part of that initiative, they had, I think, an internship program where they would ask different departments, different sort of computer science departments across the country to nominate students, and then they will interview these students and then take 4 or 5 students from the whole country. So one fine sort of afternoon, I got this email from a research scientist at Microsoft Research in Redmond saying, your department has nominated you for an internship position in Seattle, in Redmond. And first of all, I did not know that they had nominated me. And this email, like, you just get this email out of the blue and you're like, I don't know what is this about. And so, and can you meet me like in so like 7 or 8 hours? And that's like 1 a.m. or 1 or 2 a.m. India time, because this is like an interview that is happening at Seattle time. And I'm like half sleepy, like I like answered this sort of interview call. They asked me about what I was working on, and I told them about some of the things I've done. I had just written a technical paper on some of the stuff that I had done. I forwarded that to them as well. And then a few weeks later, I get this sort of letter saying, you should come to Seattle to do an internship. Yeah. So yeah, it was a very strange experience.
What I guess what can we learn from this? Just like get your supervisors to put you forward for things, or like.
So I think at that point of time, I had no plans to leave India. At that point of time, I was the idea was that I'm going to finish my undergrad studies and I will stay in India, and I wanted to be sort of close to my family and so on. And then sort of they asked me to do this, and I said, okay, like, yes, this sounds like a great learning opportunity, so I'll go. And so it's important to sort of take that initiative and sometimes leap into the unknown, because you don't know. Like at that point of time, I didn't know, like it didn't make any sense for me to sort of leave. Like I should have finished my undergrad and taken up a full-time job, but here I am, like, taking an internship in a research lab. At that point of time, I had sort of no intention of doing a PhD. And I went to that research lab, did the internship, and then they convinced me that I need to do a PhD. And then one of the researchers in Microsoft Research then was moving to academia as a professor and offered me a PhD position. So in fact, I did not even apply for the PhD position, and somehow I was enrolled in a PhD program. So like sometimes these things sort of happen, but you have to sort of just sort of go, roll with it.
Is it the case that today people who are doing well in kind of ML or CS degrees, like whether in the US or the UK or India, that they're kind of sought out by organizations like Microsoft or Google to be like kind of headhunted in a sense, or was that kind of just something that was happening at that particular era?
I think people are constantly looking. Organizations are constantly looking for the best people. People are what make organizations, right? Organizations are not like, oh, this particular building or this particular room or this particular computer. It's basically it's people who make who make an organization, and organizations are constantly looking out for the right sort of individual. And so it doesn't matter if you are sort of at MIT or at Berkeley or at some sort of a random university in some sort of random country. Or basically, you have not even done any sort of computer science education. If you sort of look at the problem from the right perspective and think about it from the right perspective, and show that you are making a contribution and you are thinking about the problem in a deep sort of way, then people will seek you out.
It seems like you've advanced up the hierarchy in Microsoft and Google pretty quickly. I guess what do you think makes someone, perhaps you, a really productive researcher?
The most important thing is to always be a student, keep learning. And part of the learning process is sharing knowledge. When you sort of share knowledge, when you collaborate with people, when you talk to people, you learn a lot.
Is there kind of a lot of socializing at DeepMind?
Like you can call it socializing, but it's more about collaboration. So be passionate about what other people are working on. Try to learn what they're working on. Try to see if there are any insights that you have that might help them in achieve their mission. I think that is the best way of learning. If you can sort of contribute to someone's success, that is the best way for you to sort of learn from them, to earn their respect, to actually contribute to the organization. So constantly, basically a constant sort of thirst for learning about what people are doing and contributing to what they're doing.
Yeah, speaking of constantly learning, I think your original background is in software verification and kind of formal methods for that, right? Was it hard to make the transition into machine learning?
So I did my undergrad in computer science, and then worked in this research group on formal verification. Then did my PhD in discrete optimization, and applying it to do inference in Markov random field or machine learning models applied to computer vision. So in fact, I did my PhD in a computer vision group where I was developing methods for efficient inference in these more sophisticated sort of models that were all the rage at that particular time. And then I moved to Microsoft Research, and one of the first sort of projects I did in Microsoft Research was in computer graphics. So for a long, long time, I was working in computer graphics and 3D reconstruction and these kinds of things. At some point of time, Microsoft worked on Kinect, the human pose estimation system in Kinect. And that is, I think, the first time I started thinking very deeply about discriminative learning and like high capacity machine learning models. So I had sort of, I was a Bayesian from my sort of PhD upbringing, but then the discriminative machine learning type of projects, I first encountered them at sort of Microsoft, and over sort of time I naturally sort of wanted to sort of combine these two sort of approaches. So I did some work, I did some projects in probabilistic programming. Alongside, I worked with a collaborator on game theory, so did quite a bit of work on game theory, applications of machine learning in information retrieval. So like I wanted to sort of learn about a lot of different fields. And so once you have worked on these sort of areas, and then you get sort of these insights from various aspects of machine learning, then when I finally sort of came into more formal sort of machine learning, it was not at all very difficult because you were working on applications, you knew already what are the problems. Yeah. So in some sense, you have a very big advantage because you know what is the issue, what like the data sets are always biased. So what kind of generalizations you would need, how would you sort of do that, what are the hacks people do to get those generalizations? Can you formalize those? So in some sense, like it becomes very easy for you because you have already been in the trenches, so you understand what are the issues involved, and then coming back to sort of proper deep learning to sort of think about like what needs to be done comes very naturally to you.
As you mentioned earlier, kind of not everyone who wants to help with AI safety and alignment, reliability, kind of has what it takes to be a researcher. I mean, I know I wouldn't. What are kind of other ways that people can potentially help at DeepMind or collaborate with DeepMind? I guess in like communications or program management or recruitment. There's other kind of supporting roles.
So like all the roles that you mentioned are extremely important. Everyone at DeepMind, from the program managers to the AI ethics group, to the communications group, is playing a extremely important and sort of necessary role at DeepMind. Like these are not optional sort of roles; these are sort of necessary roles. We were talking about specifications, right? As like trying to understand from people what do they mean by task at a fundamental level. That is a communication problem, right? You are trying to sort of induce what is it that people are after. What do they want? That is a communications problem in some sense, right? So like DeepMind is very holistic in that sort of sense, and we are not just like a bunch of people who are working in optimization or deep learning or reinforcement learning. There are people who are coming from various different backgrounds and who are looking at the whole problem very holistically.
Can you describe kind of some concrete ways that those roles like can help with alignment and safety in particular for someone who might be a bit skeptical about that?
So think about like ethics, right? The role of ethics, like what the whole ethical frameworks that have been built in the past in the literature. And a machine learning researcher or optimization researcher or some one of the best sort of students in the world who has just come out of a reinforcement learning sort of group, they might not know about the ethical sort of implications of like how research is done, or what are the biases that are there in data sets, or what are the expectations from societies, and what are and similarly like legal experts who know what are the regulations that you need to conform with, right? As at a responsible organization. So there is a very important role that all these different types of people sort of play in finally shaping up the research program at DeepMind.
Yeah, we've covered machine learning kind of career advice and study advice on the show before, so we don't have to kind of go over all of it again. But do you have any kind of unusual views about like kind of underrated ways that people might be able to prepare themselves to do useful ML research, or kind of underrated places to work, or build up your skills?
I think basically working on the real problem and trying to actually solve a problem and try to actually sort of stress test the learned model, try to break it. That's a great way of getting insights as to what the system has learned and what it has not learned.
So you're like in favor of concreteness, like trying to solve an actual problem rather than like staying in the abstract.
Yeah, I mean, you have to do both. But I think this is quite underrated. An underrated sort of approach is basically to actually try to build something, even if it's a very simple thing, and see if you can break it.
Break it how?
Like make it sort of
behave wrong.
Behave wrong.
Oh, interesting. Okay.
And then try to understand why does it behave wrong.
Oh, interesting. So if you're interested in working on alignment, then you want to like find ways that AI like becomes unaligned by accident and like actually explore that. Do you have any like concrete advice on how people can do that?
I mean, just take any sort of problem. Like you can sort of take machine learning competitions in Kaggle, or like even sort of some of the very simple sort of toy sort of data sets or benchmarks that people have, like say MNIST, right? MNIST is a very simple sort of data set and benchmark. You can try to play with MNIST and see what kinds of things you can do to the images such that the classifier stops recognizing. Even though the human would say, oh yeah, that is a 4. Yeah. Why are you not saying it's a 4? Yeah. And the model will say, no, it's I don't know, it's a 1.
Is it possible for people at home to kind of to create like adversarial examples, like do their own kind of optimizing the failure of ML systems?
You can create your sort of adversarial example by hand, right? You can just draw a picture and say, try sort of detecting this 4. If this is a perfectly valid 4, I will ask 20 people, they will tell me this is a 4, and I want to create a 4 which you will not
accept. Yeah, is that something that, I guess if someone had been doing that, you'd be like more interested in hiring them potentially?
Yeah,
like, they've got the right mindset. They're like, they're throwing themselves into it. Yeah, cool. To what extent do you think people can pick up ML or AI knowledge by doing data science jobs where it's kind of incidentally useful and kind of learning as you go, as opposed to like formally studying a PhD? Maybe do you have any comments on like whether people should definitely do PhDs and maybe who should and shouldn't?
I don't think PhDs are at all sort of necessary. I mean, they are a mechanism, and that mechanism sort of allows you to build up certain types of competencies. You get a lot of time. You are forced to basically think individually, but that can be done in many different contexts as well. Some people sort of want that kind of structure, and in a PhD, you require a lot of self-discipline, because for many people, PhDs don't work out. Because like it's very open-ended, and then you don't have that you don't without any specific structure, you might not know what to sort of do. But for other people, it basically gives you an overall framework under which you can sort of explore different ideas and sort of take your career further. But that is not a necessary sort of thing. Even in the data science sort of role, if you are really asking the right questions, and if you're really going after why is the problem working in the way it is working, and what can I make to break it, or what is the real problem? Those are the questions that you can sort of try to answer and think about in any sort of context, whether it's a PhD or a job.
Do you have any advice on what kind of people can do to stand out, such that you or other people at DeepMind would be more excited to hire them? But perhaps someone who already does know a fair amount of ML?
I think the most important thing that a person can sort of do is really think about problems which are extremely important that other people are not thinking about. So problem selection is the most important, in my view, is one of the most important things in research. Once you select the problem, yes, okay, there are a lot of different techniques, and sometimes you have to invent techniques and so on to solve a particular problem. But selecting the right problem is a very important skill to have. And so thinking about what is the right problem, what are problems that people are not asking today, what are the questions people are not asking today, but they will be asking in 2 years' time, or 5 years' time, or 10 years' time. So thinking about it in that sort of fashion will
Make you stand out.
Make you stand
I guess
out.
It's difficult, but that's why it's impressive.
And you will be ahead of the curve.
What's the best reason not to kind of pursue, a career in ML, or I suppose like alignment and robustness specifically? What's the biggest downsides, if any?
I think like at the end of the day, everyone wants to contribute to the world, right? Like you want to be relevant, and people have different sort of unique strengths. And if you can leverage your unique strength in a different way and channel it in a different sort of role, then it's completely fine. At the end of the day, like people are motivated by different sort of things, and working on machine learning is not the only way that you can sort of channel what you want to do and what you want to achieve.
So it's a question of personal fit to some extent.
Yes.
What do you think is kind of the most impressive accomplishments that have come out of DeepMind? Is it like, something like StarCraft 2, the flashy stuff that the media covers and that I'm impressed by? Or are there like more subtle things that, from a technical point of view? What impresses people inside DeepMind?
Yeah, so it's you're asking a question like pick your favorite car, and the only problem is that the cars keep changing every week, and the cars that you would be aware of have long been sort of superseded.
Oh, really? So okay.
So in some sense, basically, so you're constantly sort of say, oh yeah, I really like this stuff. Oh, next day you turn up, well, that is old news. I like this new stuff.
Yeah, interesting. So internally, it seems like things are changing a lot. Like the methods are just constantly evolving.
Yeah, absolutely. Okay, yeah. We should be surprised if that is not happening.
Yeah. Are there any approaches to robustness that kind of haven't been written up yet that your team's experimenting with?
So I think this whole idea of asking infinite number of questions, right? It's a very challenging sort of area. In the context of, say, simple models, it's hard, but you can manage it. But what does it sort of look like in the context of reinforcement learning, in the context of sort of policies, in the context of sequence to sequence models, various different types of models, various different types of applications? These are all sort of very interesting areas that we are currently sort of looking into, and hopefully we'll find something new.
So there's kind of this stereotype of like software engineers, computer science people kind of perhaps like lacking some of the soft skills that are necessary to work in an office in these big teams as people do at DeepMind, and I guess in like lots of other software companies. Do you have any ideas for how people in computer science can like improve their soft skills, like teamwork, ability to explain things to non-experts?
I think the best way to learn these kind of skills is on the job, in the sense that if you really want to sort of build these, like go and sort of try to sort of talk to someone and help them. If you are trying to genuinely help someone succeed, they will be interested in communicating to you. So even though you might have barriers and it might be hard, you will have encouragement, at least from one person on the other end, who sort of, if you can convince them that you are indeed there to sort of help them. And in some sense, just that notion of altruism, you can gain a lot from that. Because indirectly you are learning how to communicate, you are learning a completely new field. The amount that you gain might be even larger than what you have sort of contributed. So definitely sort of reach out to people and try to help them.
Are there any last things you want to say to someone who's maybe on the fence and is like, maybe I'm going to go like do this kind of research, but I'm not quite sure. Like, kind of what gets you, what excites you in the morning to come in and do this kind of research?
So it's about communication. Communication is hard. Like even humans, we constantly sort of misunderstand. People sort of have so many misunderstandings in the world, right? We are like, the world is very polarized and so on and so forth. And so people are looking at things from a different perspective. It's like everyone is right, but in their own sort of view. And so it's important for us to solve that communication sort of problem. And in some sense, that's what we are doing in machine learning. We are building a communication engine with which we can translate our wishes or our expectations to silicon-based machines. Can you express what
you really think and want?
Yes.
I guess some people they're worried about AI because it's so different from people. But I guess your angle is it's like a more extreme version of the problems that people face working with one another and like communicating between themselves and coordinating.
Yep.
That's interesting. Okay, final question, I suppose, somewhat whimsically. Imagine that things go really well and kind of ML systems are able to do most of the work that humans do, and maybe you're out of a job because they're better than you at what you do. Do you think you'd keep working hard for kind of mental stimulation, or do you think you'd just go on holiday, throw a big party and try to just have fun?
There are so many YouTube lectures and books that are on my read list or watch list that I think it will last me a lifetime, even if I start from today.
Yeah. Okay, so it's kind of intermediate, fun learning.
Yes.
Lots of podcasts and books to get through.
Yeah.
Cool. All right. My guest today has been Pushmeet Kohli. Thanks so much for coming on the podcast, Pushmeet.
Thank you.
If you'd like to hear some other and sometimes conflicting perspectives on AI reliability and robustness, the episodes to head to next are, in my rough suggested order, episode 44, Dr. Paul Cristiano, on how we'll hand the future off to AI and solving the alignment problem. Episode 3, Dr. Dario Amadei, on OpenAI and how AI would change the world for good and ill. Episode 47, Catherine Olson and Daniel Ziegler, on the fast path into high-impact ML engineering roles. And episode 23, how to actually become an AI alignment researcher, according to Dr. Jan Leiker. I hope you enjoy all of those episodes, and there'll certainly be more on this topic coming up on the podcast in future. The 80,000 Hours podcast is produced by Kieran Harris. Thanks for joining. Talk to you in a week or two.